Half the universe's normal building blocks are simply gone. This is the greatest cosmic inventory mystery of our time. We are made of the stuff that is missing. Today we are going on a galactic detective hunt, tracking down the universe's lost baryons, the protons and neutrons that should be everywhere but have seemingly vanished into the void. By the end, you will understand the ingenious methods scientists are using to find matter hidden in plain sight, and why solving this puzzle could either confirm our entire model of reality or break it wide open. We will explore sizzling invisible oceans of gas and follow mysterious flashes of radio light from across the cosmos. What does it say about our place in a universe where most of the normal stuff is hiding from us? To grasp the scale of this disappearance, we first need to understand what exactly is missing. We are searching for baryons. That word might sound exotic, but it describes the most ordinary things in existence. Baryons are simply the family of particles that include protons and neutrons. They are the fundamental building blocks of atomic nuclei. Every star that shines, every planet that orbits, every single thing you have ever seen, touched, or been made of is composed of baryonic matter. It is the normal stuff of the universe. Think of it like this. If the cosmos were a vast, dark ocean, baryons are the islands and continents we can stand on. They are solid, tangible, and they interact with light, which is why we can see them. This sets them completely apart from the universe's other great mysteries, dark matter and dark energy. Dark matter seems to be an invisible, ghostly substance that only interacts through gravity, holding galaxies together. Dark energy is the even more perplexing force accelerating the expansion of the universe itself. Baryons are none of that. They are the classical, familiar material of physics textbooks. So, we have a very precise cosmic recipe. Using observations of the ancient afterglow of the Big Bang, the cosmic microwave background, cosmologists have calculated with stunning accuracy how much total matter the universe contains. They can then separate that into the amount that should be dark matter and the amount that should be normal, baryonic matter. It is a specific number, a precise budget for all the atoms that should be out there. Here is where the mystery snaps into focus. When astronomers add up everything they can see and detect, all the stars, all the glowing gas clouds, all the planets and dust, they come up horrifyingly short. They find only about half of the baryons the models insist must exist. Not a small accounting error, but a deficit of 50%. Half of the normal matter in the entire universe has gone missing. It is as if you meticulously calculated the materials needed to build a city, purchased every brick and beam, but when you arrived at the construction site, half of your supplies had simply vanished into thin air. The blueprint says the material is there. Our eyes and our telescopes tell us it is not. So where did it all go? The universe keeps a perfect ledger. Its earliest moments, a seething cauldron of unimaginable energy, imprinted a precise set of numbers into the fabric of reality, a receipt for everything it contained. To understand the missing matter, we must first read that receipt. This comes from two key pieces of evidence, bookends of cosmic history. The first is Big Bang nucleosynthesis. In the first few minutes after the Big Bang, the universe was hot and dense enough to act like a colossal nuclear furnace. Protons and neutrons slammed together, fusing into the first atomic nuclei, primarily hydrogen and helium. The exact amounts of these elements produced depended critically on one thing: the density of protons and neutrons, the baryons, present in that primordial soup. By measuring the ancient, pristine abundances of hydrogen and helium in the oldest parts of the universe, scientists can work backwards. It is like analyzing the ash left in a fireplace to calculate exactly how much wood was originally burned. This gives us our first estimate of the total baryonic matter the universe started with. The second, and even more precise, piece of evidence comes from the cosmic microwave background. This is the faint, cold glow that fills the entire sky, the afterglow of the Big Bang itself, released when the universe was just 380,000 years old. It is not a uniform static. Tiny, speckled variations in its temperature, seen in those famous colorful maps, are like a baby picture of the universe, showing where matter was slightly more or less dense. The pattern of these speckles, their size and distribution, is exquisitely sensitive to the universe's ingredients. By studying this pattern with satellites like Planck, cosmologists can measure the cosmic recipe to a fraction of a percent. They can tell how much of the universe is dark energy, how much is dark matter, and crucially, how much is ordinary baryonic matter. The number is not a rough guess. It is a fundamental parameter of our reality, measured with stunning precision. The cosmic budget says that baryons should make up about 4.8% of the total mass energy content of the universe. Everything else is dark matter and dark energy. This 4.8% is our target. It is the amount of normal stuff, the atoms for stars and planets and people, that must be out there somewhere. So we have the receipt from the universe's birth, and it clearly states we purchased a specific amount of material. The terrifying, exhilarating mystery begins when we go to the cosmic warehouse to collect it and find half the shelves empty. That cosmic receipt was clear, but for a long time we did not have the tools to do a full inventory. The shocking realization that half of everything was missing dawned on astronomers slowly, like a fog lifting to reveal a landscape far emptier than anyone had predicted. Throughout the 1990s and into the early 2000s, teams of researchers began a monumental task, a cosmic census. They pointed telescopes at vast swaths of the universe, meticulously counting and weighing everything they could see. They added up the brilliant masses of 100 billion stars in 100 billion galaxies. They measured the faint glow of interstellar dust and the shimmering clouds of gas within galaxies. They tallied every planet, every asteroid, every speck of cosmic material that emitted or reflected light. When the final numbers were in, the result was not just surprising, it was deeply unsettling. All the glowing, shining, visible matter in the universe accounted for only about 10% of the baryons the cosmic models demanded. 90% were unaccounted for. It was like counting every person in a major city, only to realize your count was just the number of people standing under streetlights. The vast majority were somewhere out there in the dark, invisible to your eyes. This was the first concrete proof of the missing matter problem, but the plot thickened with observations of galaxy clusters, the largest gravitationally bound structures in the cosmos. These are immense cities of galaxies, thousands of them, bound together by gravity. When scientists used X-ray telescopes to look at these clusters, they saw something astonishing. The space between the galaxies was not empty. It was filled with a superheated, thin gas, a plasma so hot it glows not in visible light but in high-energy X-rays. This intracluster medium was a huge reservoir of baryons previously invisible to optical telescopes. Adding this in brought the total up, but only to about 50% of what was expected. It was a major discovery, proving that a significant portion of normal matter existed in a diffuse, hot form between galaxies. Yet even this enormous finding only solved half the mystery. The other half was still gone. The scientific community had reached a pivotal moment. The evidence was now undeniable. The universe's ledger did not balance. Half of all normal matter was not in stars, not in cold gas, and not even in the hot pools within galaxy clusters. It was simply missing from the inventory. This was the point where astronomers looked at each other and asked the question that would drive decades of research. If the atoms are not here and they are not there, then where in the cosmos could they possibly be hiding? The answer might lie not in dark corners, but in the brightest, emptiest-looking spaces between everything. The leading suspect in the case of the missing baryons is a ghostly substance called the warm-hot intergalactic medium. Scientists call it the WIM. This is not a solid, not a liquid, but a vast, diffuse web of superheated gas, thinner than the best vacuum we can create on Earth, yet spread across the cosmic void. Its temperature is the key to its invisibility. Imagine heating a gas until its atoms are ripped apart, creating a soup of bare atomic nuclei and free electrons, a state of matter called a plasma. The WIM is a plasma sizzling at temperatures between 100,000 and 10 million degrees. At such extreme heat, it does not glow in the visible light our eyes can see. Instead, it whispers its presence in two very faint signatures. First, it emits a faint, diffuse fog of X-rays, the same kind of radiation used in medical imaging. Second, and more crucially for detectives, it absorbs very specific wavelengths of ultraviolet light. If a bright, distant object like a quasar shines through a filament of this hot gas, the WIM leaves a distinct fingerprint, a set of dark absorption lines in the quasar's spectrum, like a barcode of missing light. Its theorized location makes perfect sense within the architecture of the cosmos. We believe the universe's structure resembles a vast, three-dimensional spiderweb known as the cosmic web. At the intersections of this web sit the dense galaxy clusters. Stretching between them like the silken strands of the spiderweb are the filaments. These filaments are not empty. They are the cosmic highways, the scaffolding along which galaxies form and flow. And it is within these immense, thread-like structures that astronomers believe the WIM primarily resides. Picture it as a hidden, sizzling ocean of matter, an immense reservoir of protons and ions coursing through the veins of the universe. This ocean holds the potential to account for every single missing baryon. Finding it, however, is like trying to see the heat haze rising from a distant desert road. You know it is there, you can see the shimmer, but pinning down its exact form and total mass is a monumental challenge. This faint ultraviolet whisper is the clue astronomers have been chasing. To hunt the WIM, you need a cosmic lighthouse and a supremely sensitive detector. The lighthouses are quasars, the blazing cores of distant galaxies powered by supermassive black holes. They are the brightest steady beacons in the universe, shining across billions of light years. The detector is an ultraviolet spectrograph, an instrument that does not just capture light but unravels it, splitting it into a detailed rainbow of colors called a spectrum. The Hubble Space Telescope, orbiting above our atmosphere, carries such an instrument. Its mission is to stare at these distant quasars for hours, even days, collecting every precious photon of their ultraviolet light. As that light travels across the cosmos, it passes through the vast, empty spaces between galaxies. If those spaces are truly empty, the quasar's spectrum arrives pristine. But if the light slices through a filament of the warm, hot intergalactic medium, something remarkable happens. The sizzling gas in the WIM is not neutral. Its atoms have been stripped of many of their electrons by the intense heat, becoming what scientists call highly ionized. Atoms like oxygen, heated to millions of degrees, lose 5, 6, or even 7 electrons. These ionized atoms have a very specific appetite. They will greedily absorb very particular wavelengths of ultraviolet light passing through them. Each type of ion, like oxygen missing 6 electrons, which we write as O7, absorbs a unique color. When the light finally reaches Hubble, its spectrum is no longer a smooth rainbow. It now bears dark, narrow lines at precisely those absorbed wavelengths. These are the absorption lines, the fingerprint of the WIM. It is forensic science on a cosmic scale. By identifying these lines, astronomers do not just know the WIM is there, they can determine its composition, its temperature, and even its distance along the line of sight. They are reading the barcode of the invisible universe. The challenge is monumental. These absorption lines are incredibly faint, often just a tiny dip in an already dim signal. They are easily drowned out by noise or confused with absorption from cooler gas within our own galaxy. It requires multiple observations of the same quasar to confirm the signal, And even then, each detection is just a single needle in a haystack the size of the cosmos. Every successful detection is a triumph, a tiny point of light on the map proving the hidden ocean exists. But to solve the full mystery, we need more than a few points. We need to map the entire web. The ultraviolet whisper is only half the story. To truly confirm the hidden ocean, we need to listen for its roar in another part of the spectrum, the realm of X-rays. While Hubble's ultraviolet eyes look for the WIM dark fingerprints, X-ray telescopes like Chandra and XMM Newton search for the gas's own faint glow. Picture a wire in an old electric stove. When it is cold, it is dark and invisible. But as the current flows and it heats up, it begins to emit a dull red glow, and at its hottest, it might even glow with an unseen, higher energy light. The warm, hot intergalactic medium is like that cosmic wire, heated not by electricity, but by the violent gravitational forces that shape the universe. At temperatures reaching millions of degrees, it emits not visible light but X-rays. This presents a different, equally daunting challenge for astronomers. The signal they are hunting is incredibly faint, a diffuse, almost imperceptible fog spread across vast tracts of sky. It is like trying to hear a single violin playing softly in a stadium full of roaring crowds. The cosmic X-ray background is filled with noise, from distant supermassive black holes to hot gas within our own galaxy. Teasing out the specific, smooth signal of the WIM from this cacophony requires not just powerful telescopes, but immense patience and clever statistical techniques. Scientists often stare at blank patches of sky for weeks, collecting every possible photon, and then stack data from many different lines of sight, hoping the faint signal will rise above the random noise like a shape emerging from static. Every so often, they get a tantalizing hint, a slight excess of X-rays at just the right energy that could correspond to a specific ion, like highly charged oxygen floating in the intergalactic void. These are not the crisp absorption lines seen in ultraviolet, but broad, faint humps in the data, whispers of emission. Each detection is a monumental effort, a small victory in a war against cosmic faintness. The promise of a definitive answer, however, drives the field forward toward a new generation of tools. The future of this hunt rests with observatories like the upcoming Athena mission, the advanced telescope for high-energy astrophysics planned by the European Space Agency. Athena is being designed with this exact mystery in mind. It will have a collecting area for X-rays many times larger than current telescopes, making it vastly more sensitive. It will be like switching from a small hearing aid to a massive satellite dish, finally able to clearly hear the violin in the stadium. With Athena, astronomers will not just detect hints of the WIM, they will map it. They will trace the hot gas along the filaments of the cosmic web, measure its temperature and density with precision, and finally, once and for all, weigh it. This is the grand goal, to take this ghostly component of the universe and bring it into the ledger, to see if its mass finally balances the books on the missing 50% of all normal matter. Zoom out far enough and the universe reveals its true architecture. Forget random sprinkles of galaxies scattered in a dark void. Instead, picture an immense three-dimensional spiderweb, a structure of breathtaking scale and elegance known as the cosmic web. This is the skeleton of our reality. At the intersections of this web, where the threads knot together, sit the dense, brilliant cities of galaxies we call clusters. Between these clusters stretch the filaments themselves, long, thin tendrils of matter that can span hundreds of millions of light years. And surrounding it all are the vast, empty deserts known as cosmic voids, regions of profound emptiness that make up most of the volume of the universe. This web did not form by accident. In the earliest moments, tiny quantum ripples were stretched to cosmic proportions by the Big Bang's expansion. Over billions of years, gravity acted as the great sculptor, pulling matter toward those initial ripples. Denser regions pulled in more and more material, growing into clusters. The spaces in between were slowly drained, creating the voids. The material that did not make it all the way to the clusters ended up strung along the filaments, the cosmic highways connecting everything. This is the grand stage, and it is here, within these immense thread-like filaments, that the hunt for the missing baryons reaches its climax. The stunning supercomputer simulations that model the universe's growth all tell the same story. They show a delicate, glowing latticework with brilliant knots of light representing galaxy clusters, all connected by faint, wispy strands. Those strands are not just theoretical lines. They are predicted to be reservoirs of matter, primarily in the form of that superheated, diffuse gas, the warm, hot intergalactic medium. The filaments are not solid threads, but rather diffuse rivers of ionized gas flowing along the gravitational contours of the universe. So when we ask where half of all normal matter has gone, the cosmic web provides the most compelling answer. It is not lost, it is simply in transit, or perhaps in permanent residence along these invisible highways. It is the material that gravity gathered but did not fully collect, the matter that is forever flowing toward the dense nodes but spread so thin across such immense distances that it has remained, until now, almost impossible to see. This changes our entire mental image of space. The universe is not mostly empty. It is mostly highway, a vast network of faint, sizzling rivers that contain the very bones of creation. Finding a way to illuminate this skeleton, to trace its glowing strands against the blackness, is the ultimate goal of the cosmic detectives. While the cosmic web stretches between galaxies, the galaxies themselves are cloaked in their own hidden shroud. Each spiral, like our Milky Way, is not an island floating in emptiness, but a brilliant core enveloped by a colossal, diffuse atmosphere of scorching gas. Astronomers call this the circumgalactic medium, and it is a second major reservoir for the universe's missing normal matter. Think of a galaxy not as a flat disk of stars, but as a living, breathing entity with an extended, hazy aura that reaches hundreds of thousands of light years into space. This atmosphere is unimaginably thin, 1,000,000 times less dense than the best vacuum we can create on Earth, yet it is so vast that it contains a staggering amount of material. Where does this gas come from? It is a dynamic cycle, the galaxy breathing in and out. Powerful supernova explosions and winds from intense star-forming regions act like galactic bellows, blowing huge amounts of gas out of the starry disk and into this extended halo. At the same time, the galaxy's gravity pulls in fresh, cooler gas from the intergalactic medium, which rains down, fuels new stars, and continues the cycle. This circumgalactic medium is the interface, the bustling port where a galaxy trades material with the wider cosmos. To study something so faint and immense, astronomers again turn to the technique of absorption lines, but with a closer target. Instead of looking at distant quasars, they often use bright stars within our own Milky Way or in nearby galaxies as their background lights. As the light from these stars passes through our galaxy's own extended halo on its way to our telescopes, the hot gas in that halo imprints its signature. Instruments like the Hubble Space Telescope's spectrographs can detect the faint dips in the starlight caused by highly ionized oxygen, carbon, and silicon zipping around in this million-degree corona. It is like analyzing the light from a street lamp on a foggy night. The fog itself remains invisible, but by seeing how it dims and filters the lamp's specific colors, you can deduce the fog's composition and density. These observations reveal that our galaxy is swimming in a giant, hot bubble of its own making, a massive repository of baryons that traditional surveys simply missed because it does not glow with visible light. This galactic aura, repeated around countless galaxies across the universe, likely holds a significant portion of the missing normal matter, the hidden breath of every island in the cosmic dark. These galactic atmospheres are not serene halos but stormy and violent. The gas within them is constantly churned and ejected by the most powerful forces a galaxy can muster. processes so energetic they literally shape the fate of cosmic structures. This is the engine of galactic feedback, and it is the primary delivery system scattering normal matter into the void. At the heart of this engine are two phenomenal power sources. The first comes from the death of stars. When a massive star reaches the end of its life, it does not fade quietly. It explodes as a supernova, a detonation so brilliant it can outshine an entire galaxy. These explosions do more than create light. They generate immense shock waves that rip through surrounding space, heating nearby gas to millions of degrees and blasting it outward at thousands of kilometers per second. Think of it like a series of cosmic depth charges going off in a pond, sending powerful ripples and spray far beyond their point of origin. This supernova wind carries with it a rich cargo of heavy elements, atoms like carbon, oxygen, and iron forged in the stellar furnace. It is the universe's recycling program, taking the ashes of dead stars and hurling them into the circumgalactic medium and beyond. The second, even more titanic source of feedback comes from the very center of galaxies. In many galaxies, including our own Milky Way, a supermassive black hole lies dormant, but in others it is a voracious engine, an active galactic nucleus. As matter spirals into this gravitational abyss, it heats up to incredible temperatures, releasing a blinding torrent of radiation and often launching jets of plasma at nearly the speed of light. This is not a gentle process. The energy output can be so fierce that it pushes against the infalling gas itself, effectively shutting off the black hole's own fuel supply and quenching star formation across the entire galaxy. It is a self-regulating thermostat of cosmic proportions. This process, where the energy from stars and black holes influences the gas that forms more stars, is what astronomers call feedback. It is a delicate balance. Without feedback, gas would cool and collapse too efficiently, forming stars in a frantic rush until all the fuel is gone. Galaxies would burn out in a flash. With too much feedback, gas is blown away entirely, starving a galaxy and leaving it a dormant, red and dead relic. The right amount creates the sustainable, measured pace of star formation we see in galaxies like our own. But the crucial point for our missing matter mystery is where that pushed gas ultimately goes. These galactic winds, powered by supernova and active nuclei, do not just puff up a galaxy's atmosphere. They can achieve escape velocity. They take billions upon billions of tons of normal matter, the very baryons we are searching for, and catapult them out of the galaxy's gravitational grasp entirely. This matter, now enriched with heavy elements, joins the great rivers of the cosmic web. It becomes part of the warm, hot intergalactic medium, that sizzling ocean in the filaments, or it may even be flung into the deep voids. Supercomputer simulations of the universe show this with breathtaking clarity. When you watch a simulation of galaxy formation, you do not just see stars twinkle into existence. You see great plumes of color representing these powerful outflows erupting from galactic disks like geysers. You watch them propagate through the halo, interacting with incoming gas from the intergalactic medium, and sometimes punching clear through to join the wider cosmic flow. It is a dynamic, chaotic, and beautiful ballet of creation and destruction. This connects the life cycle of a single star, ending in a cataclysm, directly to the largest-scale mystery in cosmology. The iron in your blood, forged in a supernova, was likely blown into space by such an event. That same explosive force helped distribute the universe's normal matter far and wide, hiding it in plain sight within the thin, hot plasma between the galaxies. So when we ask where the missing baryons are, we are also asking to trace the final journey of ancient stellar explosions. This distinction is absolutely critical, and it is one of the most common mix-ups in all of modern cosmology. The missing baryon problem and the dark matter mystery are two separate puzzles, each pointing to a different kind of cosmic deficit. Let us clear this up once and for all. Think of the universe as 100% pie. Observations tell us this pie is sliced into three enormous pieces. The largest slice, about 68%, is dark energy, the mysterious force accelerating the expansion of the cosmos. The next slice, about 27%, is dark matter. This is the invisible, ghostly scaffolding that holds galaxies together with its gravity. The final tiny sliver, a mere 4.8%, is the normal matter, the baryons that make up you, me, the stars, and the planets. Now, here is where the confusion often sets in. The dark matter slice is a complete unknown. We do not know what it is made of. It is not atoms, it is not protons or neutrons, it does not interact with light at all. It is a fundamental mystery of particle physics, a substance that has never been directly detected in a lab. The missing baryon problem is entirely different. It is not about that 27% dark matter slice. It is a crisis within that tiny 4.8% sliver of normal stuff. We know exactly what this matter is: protons and neutrons. The cosmic receipt from the Big Bang says we paid for a full 4.8%. But when we look around, we can only find about half of that amount. So the missing baryons are not a new, exotic substance. They are the ordinary atoms that are supposed to be here but are currently hiding from our telescopes. One mystery is about identity. What is dark matter? The other is about location. Where are the missing baryons? Solving the baryon problem would not explain dark matter. It would simply mean we have finally accounted for all the normal stuff we always knew was out there, completing the inventory of our familiar atomic universe. Finding it would be a monumental triumph of observation, proving we understand the distribution of ordinary matter. Yet it would leave the far larger and more profound enigma of dark matter completely untouched, a reminder that most of the cosmos is still made of something utterly alien to us. The most detailed maps of the missing matter do not come from telescopes, but from supercomputers. Cosmological simulations like Illustris TNG and EAGLE are digital universes, born from equations and initial conditions we believe mirror our own. They start with a smooth, almost uniform soup of dark matter and baryonic gas in the first moments after the Big Bang. Then they let the unbreakable laws of physics, primarily gravity, take over. The simulation runs for billions of years of cosmic evolution in a matter of months, tracking trillions of particles as they move, collide, and coalesce. It is a breathtaking feat of computational power, a time lapse of creation, and it tracks every single baryon. The visual outputs from these simulations are not just pretty pictures, they are predictions. When you look at them, you see the cosmic web in stunning detail. Brilliant knots of light represent galaxy clusters, but the most revealing feature is the faint bluish-white haze that stretches between them, tracing delicate filaments that span the entire virtual box. That haze is not dark matter. It is the predicted location of the missing baryons, modeled as a diffuse hot gas. The simulations show this warm, hot intergalactic medium is not smoothly spread. It is concentrated along these specific threads, the scaffolding of the cosmos, with vast empty voids in between. They even predict the temperature, density, and dynamic flow of this hidden ocean. This creates a remarkable situation. For decades, astronomers had a mystery with few clues. Now, the simulations provide an exquisitely detailed treasure map. They tell us precisely where to look and what signatures to expect. The hunt has transformed from a blind search into a targeted test. Every observation with Hubble, Chandra, or future telescopes is now a check against the simulation's prediction. Did we detect the absorption line exactly where the simulation said a filament would be? Does the measured density of the hot gas match the digital model? This turns the search for missing baryons into something far grander, a direct test of our entire cosmological model. If our observations eventually confirm the simulation's predictions, it would be a triumph. It would mean our understanding of physics, from gravity to gas dynamics, is robust enough to build a universe in a computer and have it match reality. But if the observations consistently fail to find the predicted amounts of gas in the filaments, the implications are profound. It would suggest something is wrong, not with our observations, but with our fundamental assumptions about how the universe works. The hunt is no longer just about finding matter. It is about validating the story we tell of cosmic evolution itself. That digital treasure map demands a new kind of compass, one that can sense the heat of the hidden ocean itself. This brings us to one of the most ingenious tricks in the cosmic detective's toolkit, the Sunyaev-Zeldovich effect. It sounds complex, but the principle is beautifully simple. Imagine you are listening to a very old, very quiet symphony, the cosmic microwave background, the echo of the Big Bang. Now imagine a cloud of incredibly hot gas drifting between you and that ancient music. As the delicate photons from the background pass through this hot cloud, they do not get absorbed. Instead, they get a significant energy boost. The searing electrons in the gas, moving at a tremendous speed, collide with the cooler, low-energy background photons. It is like a ping-pong ball being hit by a professional tennis serve. The collision gives the photon a kick, boosting its energy and shifting it to a slightly different part of the electromagnetic spectrum. This subtle interaction leaves a distinct fingerprint on the background radiation. In the specific direction of the hot gas cloud, the ancient cosmic signal appears ever so slightly dimmer at its characteristic low-frequency radio glow and slightly brighter at higher frequencies. It is an incredibly faint distortion, a tiny shadow and a tiny highlight combined, but it is a direct signature of extremely hot electrons. The brilliance of this method is its independence. Unlike absorption line techniques, which require a bright background source like a quasar, the Sunyaev-Zeldovich effect uses the entire sky as its backlight. The cosmic microwave background is everywhere, so you can point your telescope at any seemingly empty patch of sky and search for this telltale distortion. It is like having a uniform, pale canvas stretched across the universe. Any hot gas cloud, no matter how distant, will leave a brushstroke upon it. To catch this whisper-thin signal, astronomers build telescopes in some of the most extreme environments on Earth. High in the bone-dry Atacama Desert in Chile, the Atacama Cosmology Telescope scans the sky. At the frigid South Pole, the South Pole Telescope does the same. These locations were chosen for their incredibly stable, dry atmospheres, which are transparent to the millimeter-wave radiation they need to measure. These instruments are not traditional optical telescopes. They are exquisitely sensitive microwave cameras designed to detect the minutest variations in the temperature of the cosmic microwave background, down to a few millionths of a degree. They painstakingly scan large areas of the sky, building up a map not of light, but of these subtle SZ distortions. Each detected patch is a victory, revealing a massive reservoir of hot gas, often associated with a previously known galaxy cluster or, tantalizingly, a filament of the cosmic web. This method is allowing us to weigh the hot gas in clusters with unprecedented precision, and it holds the promise of one day mapping the warmer, more diffuse strands of the WIM itself, directly tracing the hidden skeleton of the universe with the afterglow of creation as our guide. But the cosmic web is not the only structure we need to map. The distribution of matter is clumpy, concentrated in the filaments, leaving the voids as the universe's true empty quarters. These voids are not just gaps, they are immense spherical regions spanning hundreds of millions of light years, containing only a handful of dim, lonely galaxies. If the filaments are the cosmic highways, the voids are the deserts between them, making up most of the volume of the observable universe. This presents a profound puzzle for the missing Baryons. Could a significant portion be hiding even here, in the deepest emptiness? Theoretically, yes. While gravity has done a remarkable job of sweeping matter into the web, simulations suggest a faint, ultra-diffuse mist of gas should still permeate the voids, the last vestiges of material that gravity never gathered. This gas would be even hotter and more tenuous than the WIM in the filaments, a superheated plasma with temperatures possibly reaching tens of millions of degrees. Detecting it is the ultimate challenge in faint signal astronomy. It is like trying to spot a single lit candle on the dark side of the moon. Our current X-ray and ultraviolet telescopes simply are not sensitive enough to see this incredibly diffuse glow or its absorption signature against the cosmic background. The voids represent the final frontier of the Baryons census. If we can one day probe them, we will know for certain whether every last atom has been accounted for, or if a fraction of the universe's normal matter has retreated into the deepest, darkest silence imaginable. This search pushes our technology to its absolute limits, demanding telescopes of a scale we are only beginning to dream of. These digital maps and subtle distortions now have a powerful new partner in the hunt, a cosmic siren call from the distant universe. Fast radio bursts are exactly what their name suggests, incredibly brief, unimaginably bright flashes of radio waves that last just milliseconds. They erupt from galaxies billions of light years away and for a fraction of a second can outshine entire galaxies. Their origin is still a mystery, possibly linked to magnetars, highly magnetic neutron stars. But for cosmologists, the true value of a fast radio burst is not in its explosive source but in its journey. As that brilliant flash of radio waves travels across the cosmos, it does not pass through a perfect vacuum. It slices through the diffuse plasma of the intergalactic medium, the warm, hot intergalactic medium, the circumgalactic halos, everything. And each electron it encounters along the way slows it down just a tiny bit. Lower frequency radio waves are slowed more than higher frequencies. This means that by the time the burst's entire spectrum of radio waves reaches our telescopes, the lower frequencies arrive slightly later than the higher ones. The signal is stretched out or dispersed. The total amount of this delay, called the dispersion measure, is a direct tally. It counts every single free electron the burst encountered on its multi-billion light-year journey. Since these electrons come from ionized hydrogen and helium, the normal matter we are searching for, the dispersion measure becomes a cosmic scale. It weighs all the diffuse, ionized gas between us and the burst. This is the breakthrough. For decades, we could only probe the cosmic web where a bright quasar happened to line up with a filament. Fast radio bursts are different. They are like flashbulbs going off randomly all across the cosmos. Every single one provides a clean, straight line of sight through the universe and a direct measurement of the total electrons along that path. New radio telescopes like CHIME in Canada and a SKAP in Australia are now discovering these bursts by the hundreds. They are mapping the sky not with light but with these precise dispersion measures. When scientists analyze the data from many bursts coming from different distances, a pattern emerges. They plot the dispersion measure against the burst's cosmological distance. If the space between galaxies were truly empty, the line on that plot would be flat, but it is not. The line slopes upward. The farther away the burst, the greater the dispersion, meaning more electrons were encountered along the longer path. By carefully subtracting the known contributions from our own galaxy and the burst's host galaxy, scientists are left with the contribution from the intergalactic medium itself. The initial results are electrifying. The amount of diffuse, ionized gas implied by these fast radio burst measurements is substantial. It appears to account for a large fraction, potentially even all, of the missing baryons predicted by the cosmic models. The data points are starting to cluster right around the theoretical line, the line that represents a fully balanced cosmic budget. For the first time, we are not inferring the presence of the warm, hot intergalactic medium from a faint whisper or a subtle distortion. We are directly weighing it, using nature's most energetic flashes as our illumination. The excitement in the astronomy community is palpable. fast radio bursts might finally be providing the direct observational evidence needed to close the book on the 50-year mystery of the missing baryons. They are turning the invisible cosmic web into something we can not just map but literally measure, one brilliant millisecond flash at a time. This staggering thinness is the heart of the detection challenge. We are not searching for a hidden continent but for a mist spread across an ocean. The density of the warm, hot intergalactic medium is so low it defies earthly comparison. Picture a volume of space the size of your average bedroom. Within that entire space, there might be just a single, solitary proton or electron floating in the void. That is it. This creates a vacuum millions of times more perfect than anything we can produce in our most advanced laboratories on Earth. Now imagine that same pathetic density, but stretched across filaments that are millions of light years long. The total mass adds up because the volume is incomprehensibly vast, but at any single point there is almost nothing there. This extreme diffuseness has a direct and frustrating consequence for astronomers. It means the gas emits virtually no light of its own. A handful of particles in a room-sized space are not going to glow, no matter how hot they are. They are too lonely to collide and radiate energy efficiently. This fundamental fact forces the entire field of baryon hunting to rely almost exclusively on absorption techniques. We cannot see the mist itself, we can only see how it dims and filters the bright lighthouses shining from behind it. Every detection is indirect, a study of shadows and missing colors. This also dictates the sheer, monumental scale of the observational effort. To map a web this vast with a material this thin, you need a staggering number of sightlines. You cannot point at one quasar, find a filament, and declare the mystery solved. That would be like sticking a single toothpick into a cloud and claiming you have measured the weather. To truly trace the cosmic web and account for all the mass, astronomers must conduct enormous sky surveys. They need to collect the spectra of not dozens, but thousands upon thousands of quasars and distant galaxies spread across the entire sky. Each spectrum is a single core sample drilled into the universe. Only by combining them all can scientists begin to statistically reconstruct the three-dimensional architecture of the hidden ocean, to understand its clumpiness, its temperature variations, and finally, its total weight. It is a census of shadows requiring patience and precision on a truly cosmic scale. These ghostly sound waves from the dawn of time offer another way to balance the cosmic books. To understand them, we need to travel back to the universe's first 380,000 years, a period when it was not transparent but a seething, opaque fog of plasma. Photons and baryons, particles of light and matter, were locked in a relentless tug of war, bound together by constant collisions. In this dense, hot soup, gravity acted as the great initiator. It tried to pull matter into denser clumps, but every time gravity made a move, the intense radiation pressure from the trapped photons pushed back, creating a powerful outward force. This push and pull generated colossal sound waves, spherical pressure waves that rippled outward through the primordial plasma at a significant fraction of the speed of light. These were not gentle ripples but titanic tsunamis of compressed matter and radiation, expanding for hundreds of thousands of years. Then, in an instant, the universe cooled enough for atoms to form. The photons, suddenly freed, streamed away in every direction, becoming the cosmic microwave background we see today. The baryons, now neutral atoms, were left behind, frozen in place. They stopped moving with the wave. Imagine a circular wave spreading across a pond, and at the precise moment the wave reaches its maximum expansion, the entire pond instantly turns to solid ice. The wave pattern is frozen forever, a fossil imprint of that specific moment. That is exactly what happened on a cosmic scale. The sound waves left a distinct signature, a preferred scale embedded in the distribution of matter. The radius of those frozen waves became a standard ruler etched into the fabric of the cosmos. Today, that ruler manifests as a subtle statistical tendency. When we map the positions of millions of galaxies across the universe, we find that galaxies are slightly more likely to be separated by a specific distance, about 500 million light-years, than by any other. It is not that every pair of galaxies is exactly this far apart, but that this scale shows up as a faint, overwhelming statistical signal in the data. This preferred separation is the Baryon acoustic oscillation, the BAO, the fossilized echo of those primordial sound waves. For cosmologists, this is a gift of immeasurable value. Because the physics of the early universe is so well understood, we know exactly how long those sound waves traveled before the universe became transparent. That distance, the standard ruler, is known with exquisite precision. By measuring how this ruler appears stretched or compressed in our sky at different cosmic epochs, we can trace the expansion history of the universe with phenomenal accuracy. But crucially for our missing matter hunt, the strength of the BAO signal, how prominent that 500 million light-year peak is in the galaxy maps, depends directly on the original density of baryons in the primordial plasma. More baryons in the early mix mean a stronger acoustic signal frozen into the large-scale structure we see today. So, by meticulously measuring the BAO signature in enormous galaxy surveys, like the Sloan Digital Sky Survey or the Dark Energy Spectroscopic Instrument, scientists perform an independent audit. They are not looking for glowing gas or absorption lines. They are reading the fossil record imprinted in the very arrangement of galaxies. This measurement provides a second, completely independent number for the total baryon density in the universe, a number that comes from the large-scale structure shaped billions of years after the Big Bang. And the result is a profound confirmation. The baryon density measured from the frozen sound waves matches with stunning agreement the density measured from the primordial elements and the cosmic microwave background. The early universe's receipt and its later fossil record tell the same story. There is no discrepancy in the total amount of baryons the universe was born with. The budget is correct. The crisis is not one of creation but of distribution. The BAO tells us the material was absolutely there at the beginning. Our task is to find where it has been hiding for the last 13.8 billion years. The final clues are now falling into place, and a new generation of cosmic observatories stands ready to deliver the verdict. These are not just upgrades, they are revolutionary instruments designed to see the unseen with a clarity we have only dreamed of. At the forefront is the James Webb Space Telescope. While famous for its stunning images of the earliest galaxies, Webb holds a powerful key for the missing baryon hunt, its unparalleled infrared sensitivity. It can peer through cosmic dust to capture the spectra of quasars farther away and with more detail than ever before. Each spectrum is a high-definition scan along a line of sight, potentially revealing the faint absorption signatures of the warm-hot intergalactic medium in filaments at unprecedented distances, mapping the Webb's structure across cosmic time. Then there is Athena, the advanced telescope for high-energy astrophysics. This mission, led by the European Space Agency, is being built with the express purpose of weighing the hot universe. Its huge X-ray collecting area will be dozens of times more sensitive than current observatories like Chandra. Athena will not just glimpse hints of the WIM, it will perform a full-scale inventory. It will map the hot gas in galaxy clusters, trace its distribution along the filaments of the cosmic web, and directly measure the temperature and motion of this hidden ocean. It is the tool designed to finally give us a sharp, clear picture of where the hot baryons live and how much they weigh. On the radio side of the spectrum, the square kilometer array promises to transform our understanding through fast radio bursts. This colossal network of radio dishes, to be built across South Africa and Australia, will be the most sensitive radio telescope ever conceived. It is predicted to detect not hundreds but millions of these mysterious flashes. Each one is a precise measurement of the electrons along its path. With a flood of data from bursts in every direction and at every distance, the SKA will allow scientists to create a three-dimensional tomographic map of the diffuse matter in the universe, literally charting the invisible cosmic web by the dispersion of these brilliant radio sirens. Completing this arsenal is the Nancy Grace Roman Space Telescope. Scheduled for launch later this decade, Roman's superpower is its enormous field of view. While Webb looks deeply at a tiny patch of sky, Roman will survey vast swaths of the cosmos with Hubble-like clarity. Its wide-field surveys will identify millions of galaxies and quasars, providing the essential roadmap, the sheer number of background light sources needed to statistically trace the Webb's architecture. Roman will tell us exactly where to point Webb and Athena for their most detailed investigations. Together, these observatories form an interconnected detective network. Roman provides the map, Webb and Athena analyze the specific crime scenes in ultraviolet and X-rays, and the SKA listens for the cosmic sirens that weigh the entire system. Within the next decade, this coordinated effort has the potential to achieve what seemed impossible for 50 years, to account for every last atom. We are on the cusp of either a monumental validation of our cosmic model or a discovery that forces us to rewrite it. The hidden universe is about to step into the light. Finding every last missing atom would be a quiet revolution. It would not change what we see when we look at the night sky, but it would fundamentally change our confidence in understanding it. This success would represent one of the most powerful validations ever for our standard model of cosmology, known as lambda CDM. That model, a framework built from Einstein's equations and decades of observation, makes a bold claim. It tells a complete story of cosmic evolution, from a fraction of a second after the Big Bang to the vast web of galaxies we see today. For that story to be true, the baryons it predicts must be exactly where the math says they should be, woven into the hot filaments of the cosmic web. To finally map that hidden ocean and confirm its mass would be to find the final, crucial piece of evidence. It would prove that our physics, from the nuclear forces that forged the first elements to the gravitational choreography that built the large-scale structure, is essentially correct. We would have passed a cosmic test demonstrating that we truly comprehend the life cycle of ordinary matter. Think of it as finally completing a billion-piece puzzle of the universe, where for decades we were unsure if half the pieces were even in the box. To find them all fitting perfectly into the predicted spaces would be an overwhelming relief and a triumph of human curiosity. It would mean the universe in its ordinary component is knowable and consistent. Our cosmic ledger would finally balance. With that chapter closed, our gaze could turn with even greater focus to the far more profound shadows that still linger. Solving the missing baryon problem does not explain dark matter or dark energy. Instead, it clears the deck. It removes a major source of doubt and distraction, confirming that the familiar 4.8% of the universe is fully accounted for and behaving as expected. This allows cosmologists to sharpen their questions. If we know for certain where all the normal matter is, then any gravitational effects we see that cannot be explained by it must be due to something else. The mystery of dark matter, that invisible 27% of the cosmos, becomes even more stark and isolated. We could rule out the tantalizing, though unlikely, possibility that our gravity measurements were simply miscalculated because we were missing huge amounts of normal stuff. The hunt for dark matter's true particle identity would gain new urgency and clarity. Similarly, our models of dark energy's accelerating push would rest on a firmer foundation, free from hidden errors in the cosmic inventory. In a very real sense, finding the missing baryons is the essential step toward a deeper cosmic self-awareness. It is the moment we fully account for our own substance, the atoms of stars and life, before turning to confront the truly alien nature of the universe that surrounds us. It marks the boundary between the known and the unknown, letting us stand on solid ground as we peer into the dark. But the opposite outcome carries a far more electric charge. What if, after all this searching, the final tally still comes up short? What if the universe's hidden ocean is shallower than our models insist it must be? This is not a failure, it is a doorway. A confirmed deficit of baryons would be one of the most significant anomalies in modern cosmology, a direct challenge to the bedrock of our understanding. It would force us to question everything we think we know about the stability of matter itself. The first and most profound question would be, do protons last forever? We have always assumed baryons are stable, that the protons at the heart of every atom are eternal. But what if, over tens of billions of years, they possess an unimaginably slow decay rate? If protons could decay into lighter particles, then the universe's normal matter would be slowly leaking away, transforming into something else. This would solve the missing baryon problem in a radical way by saying they are not missing, they are fundamentally gone. It would also open a stunning connection to the grand unified theories of particle physics, which predict such decay, albeit at rates far slower than any experiment has ever detected. A cosmic shortage could be the first evidence that our most ambitious theories of everything are correct, glimpsed not in a giant collider, but in the silent fading of the cosmos. The second possibility is even more unsettling. What if our reading of the cosmic receipt is flawed? The numbers from Big Bang nucleosynthesis and the cosmic microwave background are not direct measurements of ancient baryons, they are interpretations based on our current physics. If some unknown physical process in the infant universe mimicked the signals of a higher baryon density, we would have been misled from the start. Perhaps neutrinos, those ghostly particles, interacted in ways we have not accounted for, skewing the primordial element abundances. Or maybe the early universe underwent a phase transition that altered how sound waves propagated, making the cosmic microwave background pattern look like it came from more matter than was actually present. This would mean our most trusted cosmological probes, the foundations of the entire field, are giving us a subtly distorted picture of reality. Finally, there is the chance that the missing baryons are hiding in a form so alien we have not even thought to look for them. Could they have condensed into vast, dark objects like primordial black holes, smaller than an atom yet numerous enough to account for the mass? Or could they be bound up in an exotic, stable form of quark matter, a kind of cosmic strangelet that does not interact with light at all? These are not wild guesses, but serious, if fringe, hypotheses that would be catapulted to the forefront by a null result. The thrilling truth is that an empty ledger would be a catalyst. It would prove that our standard model of cosmology, for all its success, is incomplete. It would send theorists back to their chalkboards and experimentalists back to their drawing boards, not to tweak a parameter but to search for a new law. In science, a mystery solved is a victory, but a mystery that deepens is an invitation to a greater adventure. The hunt for the missing baryons, whether it ends with a map of hot filaments or a blank space in our equations, is ultimately a search for the limits of our own knowledge. This relentless pursuit of cosmic ghosts does more than map the universe. It forges new tools for humanity. The technology developed to detect a few lonely protons in a billion light-year void inevitably pushes engineering into realms once thought impossible. Consider the X-ray detectors on telescopes like Chandra or the future Athena mission. To catch the faint whisper of a million-degree filament, they need sensors of almost unimaginable sensitivity, able to count individual photons and measure their precise energy. This drive for perfection has led to radical advances in microcalorimeter arrays and silicon drift detectors, instruments so precise they can identify the chemical signature of a hot gas cloud billions of light-years away. That same exquisite sensitivity has a direct parallel back on Earth in the world of medical imaging. The next generation of low-dose, high-resolution X-ray scanners for early cancer detection and advanced CT imaging are built upon the same fundamental breakthroughs required to see the warm-hot intergalactic medium. The search for missing cosmic matter is quietly refining our ability to see inside the human body with less risk and more clarity. Then there is the art of spectroscopy taken to its absolute limit. To dissect the light of a distant quasar and find the minuscule dip caused by ionized oxygen in a filament, astronomers need spectrographs of phenomenal stability and resolution. These are not simple prisms, but complex systems of mirrors, gratings, and sensors that must maintain their calibration for years in the harsh environment of space. The technological discipline born from this need, the mastery of measuring light down to a trillionth of its wavelength, spills over into countless fields. It is the foundation for environmental monitoring satellites that track atmospheric pollutants with pinpoint accuracy. It drives advances in laser spectroscopy used to detect trace explosives or monitor industrial processes. It even informs the design of ultra-secure quantum communication systems, where information is encoded in the subtle properties of photons. The quest to read the universe's faintest barcodes is teaching us how to read our own world in exquisite new detail. Perhaps the most overwhelming technological legacy comes from the hunt for fast radio bursts. These millisecond flashes generate torrents of data. A single observatory like CHIME or the Future Square Kilometer Array does not just take a picture, it records a fire hose of raw radio voltage data, petabytes of information every single day. Sifting through this ocean of noise to find the fleeting signature of a cosmic burst requires real-time processing power and machine learning algorithms of staggering sophistication. The computing architectures and artificial intelligence models developed to find needles in this cosmic haystack are now proving invaluable for other data deluge problems. They are used to model complex climate systems, to analyze real-time financial markets, and to accelerate drug discovery by simulating millions of molecular interactions. The big data revolution in astrophysics is a proving ground for the algorithms that will manage our smart grids, our global communications, and our understanding of complex networks of all kinds. Ultimately, this flow of innovation moves in both directions. The drive to build a better sensor for a telescope often relies on cutting-edge material science, pushing the development of new superconductors, ultra-pure silicon crystals, and exotic composite materials. These materials then find their way into everything from more efficient solar cells to smaller, faster electronics. The extreme cooling systems needed to keep space-based infrared detectors functional inspire new approaches to cryogenics, with applications in preserving biological samples or enabling certain types of quantum computers. This is the beautiful, often unseen symbiosis of pure and applied science. By asking the most fundamental questions about the composition of the cosmos, we are forced to invent. We stretch the limits of measurement, of computation, of material design, and in doing so, we create a toolbox of capabilities that then filters down, transforming medicine, securing communications, and helping us manage life on a planetary scale. The search for the universe's missing atoms is, in a very real sense, helping us build a better Earth. We are beings built from cosmic contraband. The very atoms that compose our bodies, the planets, and every star we can see belong to a minority faction of reality, a mere sliver of the cosmic whole. And now we learn that even this familiar stuff is playing an elaborate game of hide and seek, with half of it existing in a ghostly, invisible state. This is not just a scientific puzzle, it is a profound philosophical mirror. It reflects the fundamental limits of our perception and redefines, once again, our place in the cosmos. For most of human history, we saw only what our eyes could show us. The universe was a celestial canopy, a stage for our dramas, with Earth firmly at the center. Science has been a relentless, humbling journey of correction. We learned we are not the center, but a planet orbiting an unremarkable star. That star is one of hundreds of billions in a galaxy that is itself just one of hundreds of billions. Our home shrank from the focal point of creation to Carl Sagan's pale blue dot, a speck of dust suspended in a sunbeam. Now, the missing Baryon mystery delivers the latest and perhaps most intimate demotion. We are not only living on a speck, we are made of stuff that the universe itself seems reluctant to put on display. The protons and neutrons in your hand right now are of the same essence as that elusive, hot gas hiding in the cosmic filaments. We are the visible tip of a vast, invisible iceberg. Our normal, tangible reality is the exception, not the rule. This forces a powerful shift in perspective. Our senses evolved to navigate a world of solid ground and liquid water, of predators and prey. They are exquisitely tuned for survival on this planet, but they are hopelessly myopic for comprehending the cosmos. We cannot see the magnetic fields of planets. We cannot feel the gravitational waves rippling through space-time, and we certainly cannot perceive a diffuse ocean of million-degree gas between the galaxies. Our entire experience of reality is a constructed illusion, a narrow band of perception filtered through biological necessity. Science, then, is our prosthetic senses. It is the tool we have built to see beyond our limitations. A telescope is not just a tube of glass, it is an extension of our eyes, allowing us to witness the birth of stars. An X-ray observatory is a new form of vision, revealing the searing heat of invisible structures. The search for missing baryons is not a niche accounting exercise. It is humanity straining to perceive a deeper layer of existence, to feel the contours of a universe that operates on scales and in states our biology never prepared us for. This pursuit cultivates a necessary humility, but also a defiant wonder. The cosmos could have been simple and obvious, a plain textbook readable by any creature with eyes. Instead, it is an endless series of puzzles encrypted in light and shadow, demanding ingenuity and patience to decode. The fact that we have come this far, that we can even formulate the question of where half the normal matter has gone, is a testament to our curiosity. We are the universe becoming self-aware, using the very atoms that are hiding to build the instruments to find themselves. So the next time you look up at a clear night sky, see it not just as a scattering of stars, but as a veil. Behind that veil lies an architecture of breathtaking complexity, a hidden skeleton of hot plasma, a cosmic web where most of the threads are invisible. We are here on our tiny world, piecing together the blueprint of a home we can never fully see or touch, and in that act of relentless searching, we find our most meaningful place within it. This grand detective story is not confined to professional observatories. You can join the search from your own home. Modern astronomy generates a tidal wave of data, images of millions of galaxies, spectra of countless quasars, and maps of the sky in wavelengths invisible to our eyes. No single team of scientists can analyze it all. This is where citizen science projects become a vital part of the cosmic census. Platforms like Zooniverse host projects where anyone with an internet connection can help. You might be asked to classify the shapes of distant galaxies, identifying which are spirals and which are ellipticals to help map the large-scale structure. Or you could scan through spectra from the Sloan Digital Sky Survey, looking for the subtle dips and wiggles that might signal a filament of the warm, hot intergalactic medium crossing in front of a quasar. Every classification you make feeds directly into the research, helping astronomers train their algorithms and pinpoint the most promising targets for deeper study. Your curiosity becomes part of the scientific process, a pair of human eyes helping to decipher the universe's hidden patterns. You can also follow the journey of the great observatories themselves in real time. Missions like the European Space Agency's Athena telescope or the Square Kilometre Array radio project have public websites and social media channels detailing their construction, their science goals, and their eventual discoveries. Watching these colossal instruments come together is like witnessing the forging of a new key to the cosmos. For a breathtaking sense of scale, dive into visualization tools like NASA Eyes. These free software applications let you take a virtual tour of the solar system, fly out to the stars and see artists' conceptions of the cosmic web based on the latest supercomputer simulations. You can zoom through filaments and voids, grasping the immense architecture that the missing baryons are thought to inhabit. It transforms abstract concepts into a navigable, almost tangible space. The hunt for the universe's missing matter is a living, breathing endeavor. It unfolds not in a single eureka moment, but through the gradual accumulation of data, the patient analysis of thousands of sightlines, and the collective effort of professionals and enthusiasts around the world. By following the news, participating in a citizen project, or simply exploring a visualization, you become a witness to this historic audit of reality. You are watching humanity complete its inventory of the ordinary stuff of creation, and in doing so, sharpen the questions we will ask of the darkness that remains. The cosmic ledger has been laid bare, and the search party is fully assembled. Our story began with a shocking deficit, half the universe's normal matter simply unaccounted for. We have a precise receipt from the Big Bang demanding a specific amount of baryonic material, the protons and neutrons that build stars and planets. Yet for decades, our telescopes could only find about half of it. The investigation led us to the most likely hiding places, immense and ghostly structures that defy ordinary perception. The prime suspect is the warm-hot intergalactic medium, a sizzling ocean of million-degree gas threaded along the filaments of the cosmic web. Accomplices include the vast, hot halos surrounding galaxies, atmospheres so thin they are virtually invisible. To find this hidden matter, astronomers have become forensic specialists using an array of ingenious tools. They dissect the ultraviolet light of distant quasars, looking for the dark absorption lines left by ionized gas. They point X-ray telescopes at seemingly empty space, hoping to catch the faint glow of superheated plasma. They use the ancient echo of the Big Bang itself as a backlight, measuring the subtle shadow and highlight of the Sunyaev-Zeldovich effect to weigh hot gas clouds. And most recently, they have enlisted nature's most brilliant flashes, fast radio bursts, whose dispersed signals act as cosmic scales, directly weighing the electrons along their billion light-year journeys. The data from these bursts is perhaps the most promising clue yet, suggesting we may finally be accounting for the full amount, but the case is not yet closed. A single promising line of evidence is not a conviction. The hunt continues as a grand synthesis, a constant dialogue between two realms. In one, supercomputers run simulations of the entire universe, predicting where every filament of hot gas should lie. In the other, teams of observers point real telescopes at those predicted coordinates, gathering photons across the electromagnetic spectrum, from radio waves to gamma rays, to test the digital prophecy. Each new observation refines the simulation, and each new simulation points to a better observation. It is a slow, meticulous process of cosmic cartography, drawing a map of the invisible. We are closer than ever to balancing the books, but until every instrument and every method converges on the same answer, the detective story remains open, a testament to our relentless desire to see the complete picture of our home. The universe's final answer is still being written in the language of light and shadow. Whether the warm-hot intergalactic medium is finally weighed to the last proton or some stubborn deficit remains, this hunt is about more than accounting. It is about completing the map of our own substance. For the first time, we are not just stargazers. We are cosmic cartographers, tracing the invisible rivers that connect all islands of light. We are learning to see with more than our eyes. Every flicker of data, every faint absorption line, is a point on a chart of a reality far grander and more hidden than our ancestors could have dreamed. Solving this mystery means we will have finally located every piece of the ordinary universe, the familiar matter of stars and life. It will allow us to stand on that solid ground and turn, with clearer vision, toward the true and profound darkness that lies beyond, the enigmas of dark matter and dark energy. That is the ultimate purpose of this search, to know the limits of our home so we can better wonder at what lies outside it. So keep looking up, not just at the pinpricks of light, but at the vast, dark spaces between them. Within that darkness, an ocean of creation churns, and our story is written in its currents. If you found this journey through the cosmic shadows compelling, subscribe for more deep dives into the universe's greatest puzzles. And let us know in the comments where you think the missing half of all normal matter is hiding. Your curiosity is part of the search too.